All right, how's everyone doing? You ready?
Pretty good.
Good.
We're doing pretty good.
Hey,
Hey,
Professor, now
what?
since you're asking, when are we having the test, the second test?
Today.
Today?
No,
Don't scare me.
it's
Jeez,
scheduled.
don't give me a panic attack like that.
What's that?
I know.
Was that not funny?
I almost had a panic attack.
Oh, I'm sorry. It's scheduled for Tuesday, a week from today.
A week from today? Are we still planning on taking the test on Tuesday?
Yeah, I think so. And I think what we won't do is we won't do 6-6 at all on that test.
Okay.
Okay. We're going to do the 5-2-3-4. We'll do that. We'll start that today and we'll finish it up on Thursday. And I think it'll be a welcome sight to see this stuff. So
Is it going to be lighter than not as heavy in math as we are reviewing this past chapter?
Yeah, the chapter 5 stuff, yes.
Okay.
That'll be because when you think about it, chapter 5, stuff out of chapter 5, we didn't have any techniques of integration yet. So any problems from those sections won't require any sort of integration that we've been doing, which is good.
Okay.
Okay, so we are going to continue where we were last time. I did send out a Dropbox link for the quiz that's due. I've made it due a little bit later today, but that was the problem. That was this problem right here that I asked you to work out. So let's go to the next problem. This is the last problem in the notes, and then I think I'm going to do 2 more after this. So let's knock this one out. This one actually goes pretty quick. So we're supposed to find the antiderivative of this. Boy, those things look really close to one another, don't they?
Mm-hmm.
They're almost the same expression, but they're not. So I have to start with long division. I start with long division because the degrees are equal, right? So put the numerator in the division box, put the denominator outside, and then you carry out the long division, right? Now, I'm not going to do the long division. Okay, I'm gonna just say, yeah, you could do that. For this problem, I actually see something we could do that would be really clever and well, clever. So I'm going to write this down.
Professor, I'm sorry. This problem, what problem is this?
This is out of the notes.
Okay.
This is out of the lecture notes. So here are the lecture notes, the problems we've been doing, and this is the last one.
Okay, got it.
So wait a minute, that's not the same problem, is it? What did I do? I accidentally wrote the denominator twice, didn't I?
You're missing the 2 on the top, on the numerator.
I put a 3 instead of a 2, and I put a 4x instead of a 3x. Well, wait a minute, hold on, let me fix that. Wouldn't this be the same? Isn't that the same thing?
That's cheating.
It is cheating. Okay, so now what I'm gonna do is I'm gonna split this integral right down the middle like this. And so what I get is all of this over all of this, which is what?
1.
1. And then plus the other one, which is x minus 1. I'm going to put those together over this. Which, by the way, is exactly what you would have gotten had you done long division. You would do 1 here, go through all the work, and then you would have a remainder of x minus 1 over the divisor. I just went about it a different way just to show you that it could be done. Okay, so here's where we are. Everyone agree? You all okay with that? Okay, so we can do these separately now. The antiderivative of x, or of 1 is just x plus, I still have to do the integral of x minus 1 over x squared minus 4x plus 3. I still need to do that. However, I'm not going to do it. And the reason I'm not going to do that is because we did that integral already 2 class periods ago. we did that exact integral. It was x minus 1 over 4x squared minus 4x plus 3. And we had a linear over an irreducible quadratic, so we made a basic U substitution. This was one of the first times I introduced you to that whole idea of trying to turn the numerator into the derivative of the denominator. So we had to multiply by 8 over 8 and bring the 8 through and split it. And then this one over here, we wound up having to complete the square and go through all this work. And then we finally got to the answer. Okay? So I'm not going to go through all that work again. I'm just going to point out that there's still a lot of work to be done on this problem. If you were starting from scratch, right, there'd still be a lot to do here. All right, so I'm moving on, all right, to a new problem. So I'm going to just pull one out of the book here. And I think one that kind of, I don't know, I kind of like this one here, x to the 5th plus x minus 1 over x cubed plus 1 dx. All right, so the first thing I'm going to do is long division, right? I've got to do long division because the degree of the numerator is bigger than the denominator. Don't know why I put a 4 there. X to the 5th plus 0x to the 4th plus 0x to the 3rd plus 0x squared plus x minus 1. So I have to have all those slot holders for those degrees of x that I don't have. All right, so what do I multiply that by to start out? What do I get here?
X
Square.
X what?
square.
X squared. Okay, then you multiply that through here and here. You'll get x to the 5th. You'll also get an x squared. That goes way down there. And then you come through and you change the signs. So subtract, subtract, carry
I have
everything.
a question here.
Pardon me?
I have a question. Can we do x cubed plus 0x squared plus 1? Like,
Oh yeah,
we
you can do that. Yeah. But you really need it more on the inside of the box than you do the outside, because it keeps track of where to put things.
Okay.
Okay, so I'm done now, aren't I? There's nothing else for me to do because I can't turn x cubed into x squared. So that's my remainder. All of that over the divisor. Okay, so my new integral becomes the integral of x squared plus negative x squared plus x minus 1 over x cubed plus 1. I can do the antiderivative of x squared. That's just 1/3 x cubed. Plus, now this integral, I'm going to have to do something. So now it's time to try the partial fractions. So what was always the first step for partial fractions after we've actually done the long division, if we needed to?
Factor.
Factor the denominator. So my question to you is, does that denominator factor?
No.
No.
X cubed plus 1 factor. It does. Okay, that is a sum of cubes. So we're used to the difference of squares, right? This difference of squares formula. We know that x squared minus 1 turns into x plus 1 times x minus 1. We know that x squared plus 1 doesn't factor. Not factorable. I'm just going to put irreducible, okay? Irreducible. But we have a separate set of formulas for x cubed minus 1 and x cubed plus 1. Those are called the sum and difference of cubes. And there's formulas for those if you don't have them memorized. They are on your formula sheet, probably way at the beginning in the algebra section. There it is, factoring special polynomials. the sum of cubes, and the difference of cubes. So what we have is x cubed plus 1 cubed. So we're going to replace the x with, well, leave x to be x, and we're going to replace the y's with 1s. So we're going to be plugging into that formula right there, the second one. Any questions there? Okay, so this should become x plus 1 times x squared minus x plus 1. Okay, that's what that is factored. So this denominator becomes x plus 1 and then x squared minus x plus 1. If you don't do that factoring step, you're going to be stuck at this point. So you've got to know that that factors out. Now what?
You can split it to A and like.
Yeah, we got to figure out all the stuff for the partial fraction. So I'm going to put negative x squared plus x minus 1 over the factored denominator x plus 1, x squared minus x plus 1. That must equal, okay, what do we have here? This guy right here is linear, and this right here is quadratic, and it's irreducible. It's not going to factor the quadratic. So that means we're going to have to put an A over our linear factor, and then we're going to have a quadratic factor here. So on top of the quadratic factor, we put linear expression, bx plus c. Now, are there any questions on this bx plus c? I want to make sure everyone understands if you have an irreducible quadratic in partial fraction decomposition, you have to put in the numerator a linear expression, not just a letter. Is everyone okay with that? Okay, so now we clear the fraction. So we multiply both sides by the denominator of the first one. So it clears out the fraction on the left. On the right, we still have the A. The x plus 1 cancels, so I have the x squared minus x plus 1 still there. And then the other one, I still have the bx plus c, and the quadratic factor cancels, but I still have the x plus 1. And I'm not even going to mess around with the short method. I'm going to go straight to the long method. So I'm going to go ahead and distribute my a through. So ax squared minus ax plus a. And then I'm going to have to FOIL the next one. So it'll become bx squared plus bx plus cx plus c. So that's me FOILing out the second one. And I'm going to collect like terms. So I have, let's see, x squared here, x squared there. When I put those two together, it'll be a plus b. I'll pull the x squared out of the back. So you have an x term there, x term there, x term there. So I'm going to go ahead and again, put a plus sign. In parentheses, I'll put the letters negative a plus b plus c, then pull the x out the back. And then all I have left there is an a plus c. And now we just match the coefficients. So I know that a plus b has to match up with the number in front of x squared. So I know that a plus b has to be negative 1. I know that negative a plus b plus c has to be equal to the number in front of x, which is a 1. So negative a plus b plus c. You just interrupt me if you have a question. Equals 1. And I know that a plus c has to be that number. So a plus c must be negative 1. I convert that over to a matrix. 1, 1, 0, negative 1, negative 1, 1, 1, 1, and then 1, 0, 1, negative 1. And then I do RREF on my calculator. And my calculator should spit out 1, 0, 0, then a number, then 0, 1, 0, and a number, and then 0, 0, 1, and a number. Anybody have those yet?
-1, 0, 0.
-1, 0, 0?
Yeah, I don't know if that's right.
Yeah, that doesn't seem right. Just think about what that would mean. If we had -1 for A and then 0 and 0, then what we'd be saying is that that whole expression just turns into -1 over x plus 1, which doesn't seem right. Maybe I made a mistake. Did anyone else try it? Did anyone else get those same answers?
I'm trying.
Okay, still working?
Yeah.
Okay, so 1, 1, 0, -1, -1, 1, 1.
I have the same matrix as you.
I got -1, 0, 0.
You got the same thing? Uh-oh, did we mess up? Did I mess up? It's been that kind of day for me, so let's see.
That's the same.
Bx squared plus bx plus cx plus c. A plus bx squared. There's no way it can be 1. I mean, there's no way that this turns into that. Oh shit, do they? Oh my God, seriously? What a stupid problem. I just pulled this problem out of the book, right?
Mm-hmm.
How dumb. Okay, it is right. I didn't think they'd give you a problem so ridiculous. So look, you see how we factored this? See how we factored this right here? Do y'all see that this and this are the same thing? They're just off by a sign.
Yes.
So you could just pull a -1 out of the top and then cancel them out. That is dumb. I mean, I would never give you a problem like that because I would want you to go through this work and actually then go after this, right? So, all right, well, let's put it down. What were the answers? -1, 0, 0, right?
Yeah.
Okay, so what is that telling us? That this is -1, that's 0, and that's 0. So that is saying that all of this in green does just equal -1 over x plus 1, which it does. I didn't see that it canceled. And that's an easy integration. Negative. So I'm going to bring my answer down from here. Does everyone understand what just happened? Does anyone have a question?
Yes. After the matrix, what happened?
So the matrix, we got that A was -1, that B was 0, and C was 0. So if we go back in here and replace the A with -1, the B with 0, and the C with 0, that kills this off completely, right? And all we're left with is -1 over x plus 1.
Understood.
And so that's the only thing I need to integrate. I was really hoping that this thing over here would turn into a nice linear expression over an irreducible quadratic, which would force us to go and play that matching game and do all that stuff. But I guess the book doesn't want to challenge us on this problem. Nevertheless, it was still fun to do the long method in the matrix and get that practice, right? All right.
Can you go over about how can we enter the matrix in the calculator?
I'm not going to do that again right now. I can do it at the end, or you can watch the video. I don't want to have to go through that whole thing again.
Okay.
Okay, let's do a different problem. Bracket, start the matrix. Bracket. That was a bummer, man. I don't like to do these problems before class because then it seems too scripted. It seems like, you know, like I don't know. I like to be surprised. That was a type of surprise I don't like though, because it was too easy. All right. Okay, this is number 34. It's the last problem in the section. Well, there's more problems, but this is the last one that's kind of straightforward. Okay, so first thing we do, we compare the degrees. So I didn't talk about this last time, but see, the denominator is not expanded out, right? It's already factored. So you have to determine the degree of the denominator by thinking about what would happen if you expanded it out. So like if I just took this part right here, x squared plus 1, and I squared it, that would give me the highest power I'd get there is x to the 4th, right? And then I still have an x out front, which would mean I distribute that through and I would have an x to the 5th. So the degree of the denominator right now is 5, and the degree of the numerator is 4. So I do not need long division. Okay, I have to establish that first. So no long division necessary. Is that all right, everyone? Okay, now I need to factor the denominator. Well, it's already factored. So I look at those and I'm going to go try to do my partial fraction decomposition now. I have a linear factor. And then I have a quadratic that's irreducible and it's repeated because it's squared, right? So that means over here, I'm gonna need, first of all, a letter over my linear factor, a over x, plus now what?
bx plus c.
Okay, so a linear expression over
X plus 1.
x squared plus 1. Then
would you add another one? So
add another one.
dx
Like dx plus e.
Plus e.
Same thing squared.
Same thing squared. Okay, so that's kind of like the little format that we tried to establish last class, you know, like what happens for each linear factor, you put a letter on top. For each quadratic that's irreducible, you put a linear on top. If it's repeated, you just have to keep writing out more and more terms until as you build up the powers. All right, well, that doesn't look fun. I may have, guess I have to be careful what I wish for here, huh? This one looks like when you get rid of the denominators here, we're gonna have quite a bit of stuff to mess with here.
This is number 34 in the book on our homework.
Number 34 in the book. All right, so there it is. I'm really hoping everyone understands how that works with the cancellation. I don't need to go through the algebra on that. But I do need to expand it. So let me work on this first. X squared plus 1 squared gives me x to the 4th plus 2x squared plus 1. But I still have to pass an a through that. So a x to the 4th plus 2a x squared plus a. All right, now I need to do, I'm gonna do this, bx plus c times that. Let's see what that is. So foiling that out, that would give me bx cubed plus bx plus cx squared plus c. Everyone understand I'm just doing the two green parts like FOIL? Just double checking it. But I still have to hit all of that with this x, don't I? So I should get bx to the 4th plus bx squared plus cx cubed plus cx. And then the last part to do is actually the easiest. I just have to pass that x through. So plus dx squared plus ex. All right, next line, I'm going to collect all my like terms together. All right, let's start with x to the fourths. Got an a plus a b, and that's it. Takes care of those. X cubes, I only have one. So plus c times x cubed. X squareds, I've got quite a few of them. So 2a takes care of that. Got plus b, takes care of that. Plus d, that's my x squareds. And then I have my x terms. I only have one x term, e times x. Oh, no, sorry, I've missed the c. C plus e times x. And then the last thing I have is an a. So that's why canceling them out as you go is useful, because then you don't accidentally forget one. I had been using colors on the previous example, right? I'd used, I think, colors to help us. But the problem is you normally sitting there taking a test don't have colors. So there you go. All right, now I set up my system of equations. So I have a plus b. What does a plus b have to be?
1.
1, the coefficient in front of x to the fourth. Okay, how about this next one, c? C has to be equal to what?
0.
0, because we don't have an x cubed. Okay, how about 2a plus b plus d? That has to be equal to what's in front of x squared. I don't have an x squared, so 0. And then, oops, I didn't leave myself enough room. C plus e must be equal to 0 also, because I don't have an x term. And then a must be 1. So we have A, B, C, D, E. We have 5 numbers, right? When we do our matrix now, we have 5 numbers and then equal to a number. So let me see, I have A is 1, B is 1, C is 0, D is 0, E is 0, and then equals 1. I don't need the equals there. And then 0 for A, 0 for B, 1 for C, 0 for D, 0 for E, 0. And then 2, 1, 0, 1, 0, 0.
Sir, I have a question.
Yeah, go ahead.
Why did you skip a line between the c plus e equals 0 and the a equals?
I don't know why I did that actually.
Okay, I thought it was. I thought it meant something.
Yeah,
My bad.
no, that was just. Yeah. I thought about that after I wrote it. I was like, why did I skip a line? But 0, 0, 0, 0, 1. Boom. There's our matrix. I mean, we could do this without. We could do this without going to RREF, couldn't we? I mean, this one, there's a lot of things we know, right? What do we know A is?
1.
Wait, A is 1. Okay. Do we know C also, right? What's C?
0.
0. Okay. If we know what A is, can't we get this first equation? If A is 1, this A is 1, then doesn't that mean B is 0? And if A is 1 and B is 0, then D should be -2. And then if C is 0, then E must be 0. So now you could do that with the RREF, okay? But I'm just showing you, with this particular one, you can just start plugging things in and figure out. Do whatever you're happier with. So these are the answers, but they're not written in order, so be careful. So here's what I have. My new integral becomes, okay, A over X, 1 over X, plus B, which is 0, plus C, which is 0. So that middle piece is completely gone. There is none of that, right? And then D is -2, so -2x over, oh, and E is 0, so just -2x over x squared plus 1 squared dx. Any questions? The first integral is natural log. The second integral is a basic u sub, right? What if you let u be x squared plus 1? then the derivative of that is just 2x and you're off by a constant, aren't you?
Yeah.
Yeah. So
So
this
that will
would
be,
go ahead.
on that side, it'll be, what is it? 1/2 natural log of, what is it, x squared plus 1 plus c?
Not natural log because it's squared. Be careful.
It'd be formula 17.
Not 17. This is a basic U sub. Look, let me pull the negative out. Let me pull the negative out and just rewrite it this way. Do y'all agree that that negative on the 2 can just come out in front of the integral?
Mm-hmm.
Okay, so now this is just a basic U sub. U is x squared plus 1. Du is 2x dx. And so this integral right here becomes 1 over u squared. Just integral of 1 over u squared du, which is the integral of u to the negative 2 du, which is negative u to the negative 1. Just basic U sub, which is negative x squared plus 1 to the negative 1. So now we could come through with our final answer, I guess. Natural log of absolute value of x. Now I had a negative sign here. Be real careful. I pulled that negative out, right? But our answer has a negative also. So the negative and negative become a plus. So this will become plus x squared plus 1 to the negative 1 plus c. Right, what do you think?
It's tedious.
Yeah. Okay, one more. One more.
Can we make it such that on the next problem, such that we have to break the polynomials kind of like the way we have it on the homework, just for practice? Something similar?
What do you mean on the homework? On the quiz?
Like on the quiz, yes. Not necessarily the same.
This one?
Yeah.
You mean the way you had to mess with this?
Yeah, or break, because we need to break the top part, correct?
Yeah, you have to break it up. You have to do like, try and turn it into what you want it to be.
Mm-hmm.
Right, is that what you're talking about?
Yeah.
I don't know. Let me do one more type of problem and then let me get into the next material. And if we have some time at the end, I'll try and do another one.
All right.
Because, I mean, I've done a few of them on video already, and then I know in the homework there's some like that. I want you to see one more kind of type of problem and then move on. So kind of a yes, maybe, if we have some time, but just not
Okay.
right now. Okay, I'm just gonna let you look at that for about a minute. And I will not play the Jeopardy music, but I'm gonna let you look at that for a minute. Okay. Any ideas?
Well, we can break the bottom piece to x times x plus 1.
Sure, you could factor the bottom. I agree. I'll do that. I mean, that is algebraically correct. You can do that. Okay.
Now, could we square top and bottom to get rid of the square root?
Good question. You are not allowed to. And the reason is because you can multiply the top and bottom by something, right? And it stays the same. So like, let me just give you an example. Let's say we have the fraction 3/4. I can always multiply the top by anything I want as long as I do it to the bottom. Multiply across, I get 15 over 20. 15 over 20 is the same as 3/4. They're exactly the same. But if you take 3 over 4 and then you just decide to square the top and square the bottom, now you get 9/16. And 9/16 is not 3/4, right? It doesn't reduce. So when you square an expression on the top and bottom, you're violating the rules. It is no longer the same thing. All right? So we're not trying, if you square the top and bottom, then you're really saying, well, what is the antiderivative of that function squared? You cannot do that. It would be nice if you could. You just square it, and then you find the antiderivative, and then square root it. But it doesn't work that way, unfortunately.
Can we add it top and bottom the square root?
You have to multiply.
What do you mean?
Multiply square root of x to both
Yeah.
numerator and denominator.
Oh, you can multiply top and bottom by root x? Yes, you could. Yes, you could. Not
But
sure
why?
it's going to get us anywhere, but you could do that.
Do the x to the 1/2, maybe?
You could change that to x to the 1/2.
Can we just go straight into partial fractions?
Well, can you? That's a good question. Can you do partial fractions? Because in order to do partial fractions, you need a rational function. And rational functions are polynomials divided by polynomials. And even though the denominator is a polynomial, right, x squared plus x, the numerator is not. The numerator is a square root function. And square root functions are not polynomial functions. To be a polynomial, the powers on x have to be positive integers or non-negative integers. So you have to have, like, the power on the x has to be either 0, 1, 2, 3, 4, 5, 6, but you can't have fractional powers. Then it's no longer a polynomial.
Can you use that thing you once, like 2 classes ago, you did, like you got a number and then distributed? Like, can you do that in terms of square root and distribute it to the function to get it and to x?
What number would you distribute?
Under root x, obviously.
Oh, you mean do the root x on top and bottom?
Yeah.
On the outside of the integral?
Yeah.
Can't do that. It can only be a number on the outside.
Take the x squared to the bottom by doing x to the 1/2, then just change it to the negative 1/2, so it will go down.
Oh, it got you. Okay, so you're saying like algebraically we could put those two together, and we can rewrite that as 1 over the square root of x times x plus 1 dx. We could do that algebraically also. We can do all that. So, I mean, mostly what y'all are saying are all valid, but I'm not quite sure that any of what's being suggested gets us to anything we can handle. So this is of course a problem I'm showing you on purpose, because the first step to this is not very natural, but everything works out great. So I'm gonna go back and I'm gonna do a basic u substitution, just a basic one. I'm gonna do use root x. Now, I know that we're supposed to see the derivative of this somewhere, right? But I'm still gonna stick with it. The derivative of this is 1 over 2 root x dx, right? And here's the part that's tricky yet nice. If I try and just get dx by itself here, I can multiply both sides by 2 root x. Now that may appear to be a problem because now on the left side, you've got x's and u's mixed up, don't you? But what is the square root of x?
U.
It's u, isn't it? So I can rewrite this line as 2u du equals dx. We kind of got lucky that we were able to replace that. So do you all agree that I can replace dx with 2u du? Yes?
Yes.
Okay. And I can replace square root of x with u, right?
Mhm.
What do I replace x with, though?
U squared.
Yeah, just take that and square both sides of that equation. U squared is equal to x, right? If you just square both sides. So now let me rewrite the integral. The part in green becomes u. On the bottom, we have u squared times u squared plus 1. And then dx becomes what?
2.
2 square root of the u.
No, just 2u, not the square root. The square root of x got replaced with u.
Okay.
Yeah? So let me put everything together. I have 2u squared on top because this u and this u come together with the 2 next to it. And on the bottom, I have u squared times u squared plus 1. And now what are we looking at? Isn't this a rational function? Isn't this a polynomial over a polynomial now? The degree of the numerator is 2. What's the degree of the denominator?
4.
4. Okay, so we don't have to do long division. So now we go and we factor the bottom. Well, the good news is the bottom's factored already, right? So now I would set up my partial fractions. What type of factors do I have here? This is a little tricky. What type of
Question.
factor?
Can we
What is
cancel
this?
the u squares?
Pardon? Oh yeah, we
Can
could
we
have canceled the u squares. That makes life easy. Oh man, that makes life real easy, doesn't it?
Could we take out the 2 and use formula 17?
Yeah, the 2 and formula 17. Shoot, man, this is not bad at all then. Man, I'm glad someone said something because I was about to go down this road right here. And that would have been twice today that I did more work than I had to. I'm having one of those days, everyone. You have them, right? You just wake up and you're just like, you know what?
Days,
You
not
just
the
want to
day.
have more days not like that. Okay, artan, we're artan, right? This is just artan of u plus c. But what's u? Square root of x, right? There it is. So the point of this problem was that a weird substitution to start actually turned it into something that we could handle. Fortunately, we could do formula 17, but had it not worked, right? Had that been on top something else or we couldn't cancel, we could have done the partial fraction decomposition, right? Now, I don't see myself giving you a problem like this on the test, but I definitely could see something like this as a bonus problem, where it's not initially obvious what to do, but then once you do it, you get a rational function, then you go and do your partial fraction decomposition. In the textbook on page 334, homework assignment for 6.3, problems 35 through 40 are just like this. And I actually just did problem number 38. That was out of the book. Okay, let's wrap this up. 6.3, let's say we're officially done. I'm gonna put up here the exam. This is the exam from a year ago, maybe this is spring 2019. So just to give you a flavor again for what I've asked in the past, I'm gonna just leave that on the screen for a second. You know, it might be wise for you to just work these problems out, you know, like.
Could you send us this? Like.
I'm not gonna, you can take a picture of the screen right now if you want to or something. I'll leave it up here for a second, or you can go back and watch the YouTube video. But I would, if I were you, you know, I would go and see if I can't handle these integrals. I think is it obvious that problems 2, 3, and 4 are all rational functions? They're all going to take partial fraction decomposition or something like that. Actually, number 2, you don't have to do partial fractions. This is a linear over a quadratic that's irreducible. So this is where you play that little matching game that Abe was talking about. But numbers 3 and 4, for sure, you're going to have to do some factoring and partial fractions. You'll have to, number 4, you have to do long division first. And even number 5 is a rational function. You've got an irreducible quadratic that's repeated. So this gives you a good, good taste of the types of integrals that I ask students to do. And number 1 is we talked about number 1. Number 1 is a trigonometric substitution. So you have to realize that that's the square root of 100 minus x squared all raised to the 3rd power, and then you do your trig sub and you have fun.
How many problems are we having for this test? 6 or 7?
Yeah, I mean, I don't think it'll be any longer than this. I mean, we are on a time restriction, right?
Yeah.
And problems do take a long time.
So
All
at
right.
least one, so we have one integration by parts, the very last one, right?
Well, on this test, I gave an integration by parts, yeah. Yeah. Okay, so let's get into the new material for today. So this idea that the topics I'm about to cover actually encompass more than one section in the book. And what I'm gonna do is I'm just gonna kind of I have my own lecture for this material. And what I've done is I've combined all the things that I think are important for us. And I present it all in one sort of tightly packed presentation, all right? So I'm going to give you your homework assignment after we're done, but it's not going to be just from one section. It's going to be from multiple sections, all right? But everything I cover should cover that, all right? Should cover what you need to do the homework. All right, so we're going to talk about something called Riemann sums. So right now, what you need to kind of think is everything you've learned up to this point has been techniques to help you find antiderivatives, right? Like if someone gives you an integral, how do we find the antiderivative? Now we try and answer the question, why? Like, why are we doing all of this? Why is it important to find the antiderivative? And it actually comes from a very classic problem, and it's the area problem. So we all know, hopefully we all know, that when someone gives us a circle, if someone gives us the radius of the circle, then the area of that is pi r squared, right? And we also know that pi is this weird irrational number. Pi is approximately 3.1415, and it keeps going forever, has no pattern to it, never repeats. It's called irrational, right? But if you take that number and you multiply it times the radius squared, that'll give you the area of the circle. So where did that formula come from, right? Where did we get that formula, right? It didn't just fall out of the sky.
The integral of
we had
the
to come up with it
circumference?
somehow, right? I'm sorry?
Isn't it the integral of the circumference? Or if you take the derivative of that, you get the circumference.
Yeah, I wonder if that's a coincidence. What Monato's pointing out is that if you want to know the circumference of a circle, it's 2 pi r. But that's also the derivative of this thing with respect to r. Like if I ask you for the derivative of this with respect to r, pi is a constant, the 2 would come out, and then you'd have 2 times pi times r, which is this. And so I wonder if there's a relationship between those. Maybe there is. Okay, but let's put ourselves back in time. You know, historically speaking, how is it that we got to this pi r squared, right? How did that all come about? Well, what could you do? Let's say that all you have are just like really good measuring devices, like you have really good straight edges and rulers and stuff like that, and you have the ability to draw a pretty accurate circle. If you didn't know pi r squared, how could you try and estimate the area of this? Anyone have any ideas on how we could estimate that area?
Well, that should be, you can basically divide the circle and then look for limits and area, no?
Okay, how do you mean? Divide it how?
Well, the circle, if you basically draw a line across and then say you make a rectangle, you can find the limits of the circumference.
If you draw up, like if you draw across and then if you keep drawing up.
No, if you, okay.
To the radius, like.
I'm not sure what y'all want me to draw. Well, let me do it this way. I think both of you are onto something here. Let me throw this idea out here. If I was really good at measuring things, could I not approximate that area by drawing a rectangle in there? Well, let's just call that rectangle 1. We should be able to find the area of rectangle 1 by measuring real carefully, right? Now, would you agree that rectangle 1, the area of that would be, I'm going to say the area of that is, no, I want to do this a different way. The area of rectangle 1 is less than the area of the circle. I'm subscripting it, right? Do y'all agree that the area of rectangle 1 is smaller than the area of the circle, the true area? Yes? Okay, so I could maybe do something a little better. Maybe what I could do is I could then measure out another rectangle. Call that rectangle 2. And then maybe another one over here, rectangle 3. I don't know, start filling in these little gaps. Rectangle 4, rectangle 5, rectangle 6. Yes? I could just keep doing that. I try to get as many in there as I can. At some point, I'd have to stop though, right? Like I would run out of the ability to measure. So if I took area of rectangle 1 plus area of rectangle 2 plus, and I did that all the way out, let's say I did K rectangles. So area of rectangle K, that's still less than the area of the circle, isn't it? It would still be less? Because I'd have all these little tiny little pieces, these little corners that I didn't account for, these little gaps, right, that didn't get filled in.
Mm-hmm.
And so I definitely know that it's not enough. It's too small still. Agreed? Okay. But I would have a number, right? This would be some number. I know that that number is smaller than the true area. So then what I could do is this. I have that number, I put it to the side. I could start over, and this time it should be pretty easy for me to measure the area of that square, right? You see that square? I know the area of that. I'll just call that area, I'll just call that the area of the square. Now, right now, do you agree that the area of the square is bigger than the area of the circle? Yes? Mm-hmm. But what I could then do is start coming in here and drawing rectangles in these little gaps and start subtracting those from the area of the square. Right? So I keep on trying to draw these in here, and man, it gets to be a pain in the butt, doesn't it? But I could do that to the best of my ability. So I would have the area of the square, and then what I do is I start subtracting from that rectangle 1, rectangle 2, rectangle 3. Now these are these rectangles, okay? I'm talking about these, not the ones from before. These are different rectangles. But I do that, and maybe I have, I don't know, I'm not gonna use K, but maybe I do M of those. Now what can you tell me about that area? Is it
Still
bigger
than
still?
that area of the circle.
It's still bigger?
I
Right?
think, yeah.
Yeah, it's still bigger because you're missing gaps again still. So this should still be bigger than the area of the circle. But this is a second number, right? It's some number. And so here's what we have. We know that the area of the circle is definitely smaller than this number that we just got, but it's bigger than the number that we got from before, isn't it?
Mhm.
So what we've done is we've smashed the true area in between two numbers. Now, the better and better I get at measuring, and the smaller and smaller my little rectangles become, the more narrow that margin becomes. And I start to smash the true area in between two numbers. Does that make sense? And so I know that the true area is somewhere in between. I've got like a margin of error. But as you might imagine, to do this precisely would take a lot of time, right? A lot of measurements. You'd have to be very precise with your measurements. It would be somewhat exhausting, wouldn't it, to do this by hand? Now, this is actually known as, this method is actually known, it has a name, and it is called the method of exhaustion. Okay, I'm not making it up. That's called the method of exhaustion. The Chinese were the first to do this with the circle, and they did it very well. And they were actually able to determine that the area of, dang it, I hate that it does that. The area of a circle is approximately 22, that's not 22, 22 over 7 times the radius squared. By doing this little rectangle thing, they were able to come up with this number right here, which is pretty close to pi. It's not pi though. 22 divided by 7 on my calculator is 3.1428. So it's the same as pi out to the nearest hundredths position. After that, it's off. But I mean, think about it, to the nearest hundredth. That's pretty good for just, you know, having rulers and straight edges and doing your best, right?
Mm-hmm.
But the idea is that if we could do the problem in a way that when we do those rectangles, that we do an infinite number of them, then we would be able to get the exact area. So here's another illustration of the method of exhaustion on a circle, but using something different. Instead of using rectangles, I can use triangles. So I could put that triangle in there. That would be an approximation. Put a second one in there, third one, fourth one, right? The area of those triangles together would be too little, right? That wouldn't be enough. So what if I do this instead? What if I have smaller triangles? Like I do that triangle and then I just start going around like this. I can always measure the area of a triangle, 1/2 base times height or something like that. But here we go. If I add up all those triangles together, that's going to be a pretty good approximation. I'm going to be off, right? I'm going to be off because of all that yellow, right? That yellow is error, E-R-R-O-R. That's error, right? I'm not accounting for that because these are straight edges as opposed to the circle, which is curved. But if I could get more in there, like if I can make my triangle smaller and smaller and put more of them in there, then I can, I hope you can see. I don't think I can zoom in anymore. That's the most I can zoom in here. But can you all still see the yellow here? I still have that little error in there.
Mm-hmm.
Okay. Let me get this back to. So the idea is that if we could have an infinite number of triangles in there, then the area of the infinite number of triangles should be equal to the area of the circle. What's the problem with an infinite number of triangles, though? There's something fundamentally that's a problem. If I tell you I'm going to put all these triangles in here all the way around, but I tell you there's an infinite number of them, what's wrong with that?
Like their calculation.
What's that?
So like since they're infinite, there wouldn't be a calculation. They will just go on and on.
Yeah, it would be impossible to calculate an infinite number, right, of things. But think more. Yeah, I mean, that is correct. I like that answer. But think more about the triangles themselves. As I add more triangles, what happens to...
The angles gets a lot smaller?
Yeah, so like if I just do a few triangles, right, then the angles here are pretty big. But if I start doing more triangles, right, more and more and more, what's happening to that angle? The angle is
becoming smaller, smaller.
It's getting smaller. So if you had an infinite number of them, wouldn't the triangle actually just converge on itself and become just a single line?
Mm-hmm.
And you can't calculate the area of a line. The line has no area. It only has a length, right? So we have several issues here. We have one, that the area starts to go to 0, right? As you get more of those in there, the area goes to 0. And you have the problem that you have to calculate an infinite number of things. So it's like a double-edged sword. Two things are a problem, right? Well, that's what makes calculus so beautiful, is that we have a way of doing it still. We have a workaround. We have a way to get the answer. We can solve all those problems that appear to be unsolvable. This area becoming 0 and the infinite number of computations, we can still do them. Now, how do we do them? We do them with what we learned in Cal 1, the heart of calculus, the basis of everything we do in calculus. That's the limit, right? The limit always allows you to head somewhere, right? Go to 0 or go to infinity and still get a numerical answer, right? An answer that makes sense. And that's exactly what we're going to do here. We're going to talk about the area of each of these, right? We're going to be like, okay, if I could just figure, I hate this thing. If I could just figure out what the area of that one is, like a formula, and then take the limit as the number of those go to infinity and see if I get a numerical answer. So that's kind of the gist of it. Y'all understand like the underlying kind of like motivation for it? And then the approach. Okay. So here we go. We're going to step away from the circle. We will revisit the circle again. I will actually prove to you where pi r squared comes from later. Like we will calculate it. We will do it ourselves. Okay. But for now, I'm going to skip through all this stuff. I'm going to get just to where I want us to go with this today. And that is a simpler problem. Well, actually, it's not a simpler problem. It's a more general problem. So the ultimate question became this, all right? Let's say that we have a curve. We'll call this y equals f of x. And let's say that we want to start at some point A, end at some point B, and take a look at that function right here from here to here. And then imagine dropping lines straight down to the x-axis and then asking ourselves this question. What is the area below this curve?
So is this the under the curve area problem?
Yes. So that's what we want to know. What is the area? Well, how does this tie into the circle? Well, here's how it ties into the circle. If I have a circle, right, I could just look at the first quadrant of that circle. Now, is that first quadrant of a circle a function? Is it a curve? Is there a curve that goes with that? Yes, right? Now, if I look at that, then I can look between 0 and whatever the radiuses are, and I can say, what's the area under this curve, right? So would you agree that solving this problem up here, this more general problem, if we could figure out a way to do this, then we could solve the circle problem? because we just need to figure out what that curve is and then find the area. Yes?
Mhm.
So it's actually
And
going to
then
be more
add
powerful.
them together.
Pardon?
And can we all add them together, like in the terms of circle?
Yeah, then if we found the area of the yellow, we just multiply by 4. Right?
Oh, okay.
Because
Yes.
we know it's symmetric. So this general look, okay, this general idea of finding the area below some curve. Where the hell's my mouse? Come here. Oh, hold on. So this general idea of finding the area below a curve is very powerful. It will allow us to do the circle, it will allow us to do a lot of things, okay? Now, the question is, how do we do it, right? How do we actually go about doing this? So here's the way I want you to try and visualize this. We're going to do not triangles like we did with the circle, we're gonna do rectangles. Kind of like we did with the first part of the circle. You know how we were drawing a bunch of rectangles in there? But we're gonna be much more systematic about how we do it. I'm going to, let's just go with the very basic example first. I would like for us to approximate the area under this curve with one rectangle. Okay, so let's just try this with one rectangle. And please understand that we know what the function is, okay? So the function has been given to us. So it might be the function x squared, it might be sine x, it might be some weird rational function, whatever it is, that function's, we have it, okay? So if I need to plug a number into it, I can. So let's say we have this function. Let's say that someone gives us what a and b are. So everything in green is given to us. Then if I wanted to approximate the area of the yellow with something, I could just draw a rectangle that goes here, right? Like that rectangle. That would be that approximation would suck, I agree, but it would be an approximation, right? So can someone tell me what the area of that rectangle is? What is the area of that rectangle? What is that area of that rectangle? So
Base times height? Or?
Base times height. Do you know how tall it is?
Yeah,
How
we can
tall?
find out.
We would have to plug in what number into the function? Well, I took this height, right? Isn't this the height
B.
right here?
B. You have
So
to
it doesn't
plug
look like I
in B.
plugged B in, right? I plugged B into the function.
Mhm.
So the height of this thing would be equal to the function evaluated at B. So the height is f of B. Now times, now how wide is it? What's the width?
B minus A.
B minus A. It's the difference between those x coordinates. So that would just be B minus A. Now, again, if someone told me what the function was and they gave me B and A, couldn't I actually calculate this? Right? I could, right? Now we get a number as an answer. So I'm going to say, okay, yeah, I could do that. I could do one rectangle, be no problem. Okay, but one rectangle sucks. So why don't we get a better approximation? Why don't we do 2 rectangles? So the way I'm going to do 2 rectangles is this. I'm going to do it in a different color. I'm going to go right halfway, right in the middle. I'm going to go up to wherever I hit, and then I'm going to go straight over. That'll be rectangle 1. And then I'll go to the right end point again. I'll go up and straight over and down, and that'll be rectangle 2. Now, which approximation was better? Just one rectangle or having both of those? Which is a better approximation? What's that?
Having both?
Having both, because you reduce some of the error, don't you? Do you see how some of the error goes away? And what would be better than 2 rectangles? 3. What would be better than 3? 4, right? Now I'm going to illustrate this with a visual here. This is kind of what I'm doing here. Let's see if you can see this. So we have a function here. It's the blue function right here. I'm looking between, I know it's hard to see this, between 1 and 5. And I'm approximating it with this rectangle that goes up and over and down, right? And that area is not a very good approximation of this area underneath that curve. It actually sucks pretty bad, doesn't it? But I could do more than one rectangle. I could do 2 rectangles. Hey, stop. What's going on here? I could do 2 rectangles. Okay. So instead of 1, I go halfway. I go up, over, down, up, over, down. That's a better approximation, right? Because I have less error. I could do 3 rectangles. Even better. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? I can just keep going and going and going and going and going, right? The more I do, the better this gets, right? The error starts to vanish away. Ideally, I'd like to have an infinite number of rectangles. But just like with the circle, what's the problem with an infinite number of rectangles? What happens to their widths?
Decreases.
Starts to go down, right? Approaching 0. Okay. Does everyone understand what I'm trying to do here? Any questions on this? All right. Let's go back to this example. All right. Let's finish this up. Tell me what our formula would look like if I wanted to do those 2 rectangles. All right. So what would be the area of the first rectangle? This is real important that you understand this. What's the area of the first rectangle?
Length into breadth.
How tall is it?
B.
This first rectangle, we went halfway and went up and over, right?
Mm-hmm.
Okay, so what's halfway between B and A?
B minus A divided by 2?
B minus A over, or not, that's close, it's not.
A plus B minus 2. Divide by 2, my bad.
Yeah, so if you ever want to find a number right in between 2 numbers, you take their average. Okay, this is something I remember as a student. I was like, what? So like if we have the number 3 and then we have the number 5, if I want to find the number right in the middle, which is 4, right? We don't have to think about that. To get it, all I do is add up 3 and 5, that's 8, and divide by 2. So I take their average, and that gives me 4. Understand? Okay. So this is the number B plus A over 2. Okay, so that's what I plugged into the function, right? That's what I plugged into the function. All right, so this would be F of B plus A over 2. And then I have times, now how wide is it? What's the width of this rectangle?
B plus A
over 2.
B plus A over 2 minus A.
Minus A.
Isn't it? That would be like, just like on the previous one, it was B minus A was that distance. Here it's B plus A over 2 minus A. And then I could go find the area of rectangle 2. So how tall is rectangle 2?
B.
So
F of B, right? The function evaluated at B. How wide is it?
B plus A divided by 2 minus B.
It would be the other way around. B minus this one. So B minus B plus A over 2. Now remember, we know the function and we know A and B. So we could go calculate these, couldn't we? Like by hand. But again, this would suck, right? This would suck because that would be a lot of calculations to do, wouldn't it? That'd be a lot of calculations to do. All right. And if we wanted a better approximation, we would have to do 3 rectangles, right? And even better would be 4 or 5 or 100 or 1,000 or 1,000,000. And I would hate to have to come up with this formula for all 1,000,000 rectangles, right? Or all, yeah, 1,000,000 rectangles. So I'm going to clear the slate. I'm going to start over, and we're going to do this more systematically. And we are going to come up with a formula, and the formula is going to be pretty damn awesome. All right, here it is. So that was just to get you kind of thinking about how we're going to approach it. Here's our function. I'm going to start us out here at A and end us here at B. And this is our function y equals f of x. Now, let me do this. Imagine now that we cut this into n rectangles. N rectangles. So I'm not telling you how many, right? So maybe we have one here. I'm gonna do a different color. We have one here. By the way, these are all the same width, okay? So they're equal widths. And we have a bunch of them in here, and then we have our last rectangle out here. Okay, so I'm not telling you how many, we just have n. All right, first things first. They all have the same width. Do you agree with that? They all have the same width. How wide are they?
A plus B?
N.
Not n. So sometimes it's easier to do a specific example under this. What if I took the interval 3 to the interval 8? And I told you to cut that into n pieces. How wide would each one be? So imagine this is cut into n pieces.
It'd be 3 plus n. 3 plus
Is it 3 plus
n?
8 divided by n?
8 minus 3 divided by n?
8, it would be this number 8 minus 3, right? That's 5. So that means that you would have the distance from here to here would be 5, right? And you're going to cut that into n equal pieces, right? So you should have 5 divided by n.
N.
Agreed? 5 divided by n would be the width of each of the rectangles. So each of these widths, I'm just going to grab one of them. The width of this, which means the width of all of them, is the b, take away the a, and divide by n. This is the width of each rectangle. Each, all, okay, you can say all rectangles. So that's good, right? I mean, in terms of formulas, if I were to be looking for the area of rectangle 1, I'm not quite sure what I'm going to plug into the function, but I can tell you that its width is b minus a over n. And same with rectangle 2. The area of rectangle 2 would be the function evaluated somewhere, but then I know the width is b minus a over n again. So do y'all see that? This is the width, and then each of these are going to be the height. But the height depends on where you are, right? The height does depend on the rectangle. Do y'all agree with that? Yeah?
Yeah.
Okay, so let's talk about what we plug in. So I want us to focus our attention on rectangle 1 right now. We're going to go to this right endpoint. We're going to go up. We're going to plug that number into the function, and that's going to be our height. Can somebody tell me what the x coordinate of that is? So remember, this point right here is A, right? That's A right there. So we're not at A, right? We're not at A? Where are we?
A plus b minus a over n?
Exactly. We are A, but then we're adding one width of a rectangle to it, aren't we? One width of a rectangle. So watch the way I write this. This is critical. This is going to be A plus one width. So I'm going to put 1 times b minus a over n. So it's A, and then I'm adding one rectangle width, and that'll take me to that endpoint. A plus one of the widths of the rectangle.
But
Okay,
how
what
is
about the
it
next
the height?
point? Pardon?
How is it the height then?
Because that is the point that we're plugging into the function. Once you plug that point into the function, it spits out a y coordinate, doesn't it?
Yes.
And that y coordinate is exactly that height right there.
Yeah, I'm sorry. That was a dumb
No,
question.
good question. Understand?
Mm-hmm.
Okay, so for rectangle 2, we want this point. So what's the x coordinate there?
A plus 2 into b minus a over n.
it's A, we start at A, but instead of jumping to the right once, we jump to the right twice. So it's plus 2 of those B minus A over N's. Make sense? The next one would be what? A
3.
plus 3 of the B minus A over N's. And then
But
4
this-
and then 5.
But this can go on like, I don't know, as,
It can go on N times.
yes.
N times, because we have N rectangles.
And then we
A-
won't have an exact calculation for it.
Hang tight. It's coming. Don't worry. It's coming. I just want to be able to build the formula first. So the third rectangle, the area of that should be the function evaluated at A plus 3 jumps of B minus A over N times the common width that we had. And that would happen for every single one of these, right? Every single one of these.
Mhm.
Okay. So someone tell me this. What would the area of the nth rectangle be then? Because remember, we have n rectangles. What would the area of that be? It would be the function
A plus
evaluated
N,
A plus how many jumps?
N
N jumps.
into
times
B minus
B
A over
minus A
N.
over N. Then times the common width, right?
Yes.
The reason I like to show that last one is because check out what it is. The n's cancel. And then you have A plus B minus A. What's A plus B minus A?
F of B.
F of B. Isn't that the right endpoint? So this last rectangle takes that last right endpoint right there. That's that last one. I'm sorry. Ah, shit. That right there is really just F of B. I'm just pointing out that the formula seems to be working, right? When we get to that nth rectangle, we're actually at the very end of the interval, and so we should have the height at the end point. All right.
Isn't N getting added to A? Like, how can you cancel the N's out if
That's
there's
multiplication. This is multiplication right here.
okay, and the plus is with A, not okay. Yeah,
Yeah.
my bad.
Okay. So, where are we? If you look at all of these formulas, all of them, the only thing changing within the formulas is this number. Do you agree? Everything else in the formula is exactly the same. Exactly the same. So we're going to switch up our notation now, and we're going to introduce a new notation called sigma notation. Now, I know some of you are familiar with this. Sigma notation is a notation we use whenever we want to do sums. So if we want to do whenever we want to add things up. Let me do it this way. Let's say that I wanted to take something, we'll call it a sub 1, and then add it to a sub 2, then add a sub 3. Let's say we had, like, I don't know, 100 things we wanted to add up. I wouldn't want to write that down 100 times. So what we do is we rewrite it as sigma, capital Greek letter S. We put k equals 1, and then up here we put 100, and then in the expression here we put a sub k. So the way this works is that the sigma tells you you're going to add a bunch of stuff up. K says where you're going to start. Up here tells you where you're going to stop. And then this is the expression that is going to change. So you start with k being 1. If I replace this k with 1, I get a sub 1. Then I say plus, and then I increase this k by 1 integer to 2. So I put a sub 2, I put it here, and then I put plus, and then 3, and then 4. Have you all seen that before, this notation? If you haven't, then we may have to meet in office hours to go over that. But with this notation, do you agree that I could write this? The area of all rectangles, all n rectangles, is sum k equals 1 to n of a sub r sub k. So look at this is a sub r 1, a sub r 2, a sub r 3. So I'm just going to add up all of these guys together. Y'all agree with that? But this is just equal to the sum k equals 1 to n of f of a plus k times b minus a over n times b minus a over n. So what I'm pointing out here and what I'm hoping you're seeing is because this is the only thing that changes in each of these formulas, if I replace everything in green here with the k, then this notation is just me adding up all these things. So if I let k be 1, this becomes f of a plus 1 times b minus a over n times b minus a over n. That's the first rectangle. If I let k be 2, so I say plus, and now I do 2 here, then that's the second one. Then 3, that's the third one. And I keep doing that until I get to the nth one. Do you all agree with that? You don't have to be able to do any of this. This is really to get you to understand what I'm about to tell you. So you see this right here?
Mm-hmm.
This is the approximate area. That's the approximate area, isn't it? It's not the true area. Why is it not the true area?
Because of errors?
Yeah, we got a bunch of errors, right? We stopped, didn't we? We stopped. We said, let there be n rectangles. So how do I get the true area then?
Take the right Riemann sum and subtract it from the left Riemann sum.
I'm sorry, I didn't hear that. What?
You can take the left Riemann sum and the right Riemann sum, or the over and the under, and meet at an average.
Okay, so that would be one idea. You could do it like an upper and a lower, but just more in general, like layman's terms, how would I get a better approximation? Let me ask that question. How would I get a better approximation than this one?
So can you put limits on the, and divide and then take it by parts, like we did for the circle?
Kind of. I'm going to say your answer kind of because you said the word limit. That part of it I agree with. Look, a better approximation of this would be if I just had one more rectangle, right? And a better approximation of that would be if I had another one. So what I really want to do is let the number of rectangles become what?
Would it be the limit as n approaches infinity?
There we go. We want to do this formula that I just boxed up here. We want to take that formula and we want to ask ourselves, what is the limit as n goes to infinity of the sum k equals 1 to n of f of a plus k times b minus a over n times b minus a over n. What is that limit? Whatever that limit is the true area. That is the true area, everyone. Now, we have 10 minutes, okay? So we're not going to be able to get into this any deeper. But I'm going to now share with you, well, let me back up because I know I'm moving fast through this. We started with the function. We said, what's the area underneath it? We said, okay, well, we could just cut it into rectangles. All right, if we do that, we could find the area of each one. But you know what? That's a pain in the ass. And then we said, well, you know, maybe we could come up with a more systematic way. Maybe we could get a general formula for the area. And then we were able to do that in a way that we could rewrite it in sigma notation in a nice condensed form. And then all we're saying to ourselves is, okay, what happens to this sum if you let that number right there, n, go to infinity? And for a long, long time, this was a known formula. These are called Riemann sums. The problem with Riemann sums is you have to calculate these. You have to evaluate this limit, and it is very difficult sometimes to evaluate this limit. But then came the fundamental theorem of calculus. The fundamental theorem of calculus. All right. This, now you may not know this, but there's actually a fundamental theorem of arithmetic. There's a fundamental theorem of algebra, and there's a fundamental theorem of calculus. So two of them you've already seen, but you probably don't remember. Well, the theorem of algebra you probably never saw because it involves imaginary numbers, so you usually don't see it. But the fundamental theorem of calculus, basically there's a couple of versions. The version that I want us to focus on says this. Says that the area under y equals f of x on some interval a, b is capital F of b minus capital F of a. Now, what is capital F? Where the derivative of capital F is equal to little f. Okay, so let me explain what this is saying. It's saying if you want to find the area below a curve, okay, below some function f of x, all you have to do is find the antiderivative of that curve, the antiderivative of that function, which we are calling capital F of x. And then just evaluate that antiderivative at two endpoints, at the two endpoints, and that gives you the area. Okay, so this is a theorem. I'm not proving this theorem, okay? You have to take this theorem on faith. But this is a huge, huge result, all right? Huge result. So how do we write this down? How do I tell you that I want you to go find the area under a curve between two endpoints? We have notation for this. Don't worry, this will all come together in an example in just a moment. Okay, so I need to tell you that I want you to find the area underneath the curve, and I need to give you the interval, right? I need to tell you A and B, and somehow this is tied into the antiderivative because of the fundamental theorem of calculus. So here's what we're gonna do. We're gonna go back to this notation that I introduced you to many, many, many weeks ago. You remember this? What did that notation mean? That right there says to you, go find the antiderivative, right? That's what it says. So for you, you know that this means find the antiderivative and add a constant to it. You've been torturing yourself for weeks with this, right? Mm-hmm. What we're gonna do now is we're gonna add something to this. We're now going to say, look, we have an interval that we're going to be looking at, and we want the area underneath this curve. So we're going to add to this notation A and B. That's called the lower limit and upper limit of integration. I'll write that down later, don't worry. Then we put the function dx, but now we actually have a way to compute it. And what we do is we take the antiderivative, we plug in B, and then the antiderivative, and we plug in A. And this is going to be a number. And that number is the area. This is the fundamental theorem of calculus. And this is also referred to as a definite integral. Where this one right here is called an indefinite integral. We call the top one an indefinite integral because our answer is a function. Right? This is a function plus a constant. So this gave us a family of answers, right? That was a family of answers. But this here is a definite integral because it's going to give us a numerical answer that represents the area under the curve. Okay, we are doing an example, but now I can finally show you where this notation comes from. That integral f of x dx. Okay, deep breath. Go back to the previous page. See this I have boxed here? Okay. All of this crap right here is a sum, right? That's a summation, but it's a special sum because we're taking a limit of the sum. And so we have a notation for that. The notation for the limit of a sum is this symbol, the integral symbol. All right? Do you all see that this part is just the height of the function? And that's just the function evaluated somewhere, right? And do you all see that this right here is the change in the x? The whole time, it's just how much we're moving over x by every time, right? That's the width of each rectangle, right? So I wish I had these both on the same page. This right here is just the function evaluated at some point. And this right here, that's our little tiny infinitesimal change in x, isn't it? So we'll call it dx. So I'm trying to get you to see that this formula that you've been working with the whole time just means that we are going to take an infinite, a limit of a summation of the height of a function times its width, and that will give us the area. I will pound this in more later because we're going to need to understand how the structure of what's in here helps us solve problems. But I think with the last 3 minutes, we should do an example. So I'm going to do a very simple one. Y is equal to x on the interval 0, 2. Find the area. All right, I have to move fast because I have 2 minutes. Do we all know what y equals x looks like? That's y equals x, right? Okay, I only want to look at the interval 0, 2. I want to find the area underneath that. Now, I gave you a straight line for a reason. Gave you a straight line because we can find the area right now without any calculus. Can someone tell me the area of that triangle? How wide is it?
1 over 2 into h.
That's 2, right? How tall is it?
2.
2. Okay, so area is going to be 1/2 base times height.
Yes.
Or 1/2 2 times 2.
Which is 1 over 2. Yeah.
Right?
2.
It's just 2. But that's not using any calculus because it was a straight line. Now let's do it with the calculus. What we want to know is what is the limit of the sum of the function x if we look from 0 to 2. Do you see that notation now? We've added the 0 and the 2.
Mm-hmm.
Well, that means what we need to do is find the antiderivative. Let's find the antiderivative. What is the antiderivative of x?
X squared over 2.
X squared. So here's what I recommend you do, and I'm going to do this from here on out. I'm going to write down the antiderivative, x squared. But I'm not, oh, sorry, 1/2 x squared. But I'm not going to put plus c. Because this is a definite integral, because I have these numbers here, what I'm going to do instead is put what's called an evaluation bar next to it. And I'm going to put 0 down here and 2 down here. So that first thing I write is just an opportunity for me to write down what the antiderivative is. And then that bar is reminding me I still have work to do. I have to plug in 2 into this answer. So we always start by plugging this number in first. So plug 2 into this. Once you figure out what that is, you will subtract from that whatever you get when you plug in 0. So what do you get?
2.
2. And that's not a coincidence. That's not a coincidence. That is the fundamental theorem of calculus. But the great thing is now this works for any function, not just straight lines. It works for all curves. Okay, I've tried to get through as much. This mostly today was just about the buildup, like where it comes from, where the notation comes from, the Riemann sums, the fundamental theorem of calculus. From here forward, what we're going to be doing is using the formula to now find areas under curves. So in your homework, let me look at what you could do. Do y'all see that there's really only just one more thing added on? Like all we're doing now is you're still finding antiderivatives, but now you've got to plug in these 2 endpoints and get a number. So from 5,2, let me see if I want you to do anything in 5,2. How about for 5.3? This is the only thing I want you to worry about tonight. We'll come back and do more. From 5.3, this is page 289. Look at like the first 10 problems, anything through the first 10. And let me just throw up an example of one of these so you can see the type of problem you're looking at doing. Okay, so that's an example of one of the problems. So all you have to do here is realize you've got a definite integral. So you're going to find the antiderivative of this, which everyone here should be happy to see something like this. Find the antiderivative of this. Plug what number into it first?
0.
0, and then subtract from that what you get when you plug in -2. Whatever that number is the answer we're looking for.
Wouldn't it be 0 if you plug in a 0?
It would. Well, you have to look at the antiderivative first. Also, someone's going to ask me, and I know we got to go. When I did the 1/2 x squared, someone's going to ask me why I didn't put plus c. And the reason plus c doesn't matter is because if I plugged 2 into this, I would have had a plus c here. And then when I plugged the 0 in here, I would have had the plus c here. And then when I subtracted, they would have canceled each other out. So the c always goes away within the actual subtraction part. So you don't need to write plus c.
When there's limits.
When there's numbers here, that's correct.
Yeah.
When it's a definite integral like this, you don't need the plus c. When it's an indefinite integral, like everything we've done up until today, that you need the plus c. All right, we'll get more practice with this. If you feel weird about this, just make sure you're getting your 6.3 homework done, all right?
Sir, before we go, question, the quiz is due today. Just to make sure, the problem that we have to do is the integral of 2x squared minus x plus 4 over x cubed plus 4x, right?
That's it right there.
Cool. Okay. Thank you.
Anything else?
Also, I have a question. So for the exam, we have it on Tuesday, right?
It's scheduled for Tuesday, which means we're only going to meet one more time before the test.
Okay. Oh, yes.
Yeah. And you know what? Like, if you look at this exam, okay, where does what I talked about today come into play?
Nothing.
The last two problems.
Oh.
Right. So you have to go do all this, right? You have to go find the antiderivative of that. You've got to use your, whatever method you have there. That would probably be partial fractions. You do all that, you find the antiderivative, right? Then once you find the antiderivative, you plug in 1.
And 0.
Whatever you get, write it down, plug in 0, write it down, subtract the 2, you have a numerical answer. So there's not a whole lot of, we're not adding a whole lot, right? It's just an evaluation step at the end where you actually plug a number into the answer.
Okay. And can you go over, because I'm getting an error when I plug in my numbers for the matrices in the calculator.
Yeah, I can write down what you're supposed to have. You have to tell me what matrix you're trying to do. Another question?
No, I guess we don't have time to go over a problem like the one or the quiz.
Yeah, I have to be somewhere at 3:15, so
no problem.
I'm limited on my time, and I have
so what happens if we get it wrong?
Pardon?
The problem on the quiz. What happens if we get it wrong?
It depends on what you did, I guess. I mean, you get some partial credit as long as you're doing the right. Was it the question you were asking me? Yeah, I think the quiz.
How to decompose the polynomials?
Well, you need a 2x up top, don't you? Because you have some. I think you need a 2x on top.
Mm-hmm.
So just multiply the outside of the integral by 2 over 2, and push the 2 into the top. What do you have in your numerator?
2x squared.
That's what you have when you do the partial.
That's what the problem says. No, in order to split the top and bottom. So we
You
need
did this,
to,
right?
yeah.
You found A, B, and C?
No, the problem is how do we decompose? Because aren't we supposed to, yes. So aren't we supposed to divide, find two factors for 2x squared minus x plus 4?
No, you don't need to factor the top.
Okay.
You only factor the bottom.
Okay.
All you do is factor the bottom, which is this, and then this is where you do the partial fractions. You don't have to do anything to the top.
Okay.
Is that what you're talking about? Are you trying to factor this?
Yes.
Yeah, no, you don't need to. The only thing you ever have to factor with partial fraction decomposition is the denominator.
Okay, I thought we're supposed to.
That tells you what to put over here.
Okay.
So at the end, what we have to do is, okay, so we have to use U sub, but we also have to.
So why can't we use a trig sub here?
Sure.
After you take the antiderivative of 1 over x.
Like right here?
Yeah.
A trig sum on that?
Yeah.
What's your trig sub going to be? Like, how are you seeing this as a trig sub? Are you rewriting the denominator as the square root of this stuff squared?
Okay.
Right, because it'd have to have the square root of, it would have to be one of those forms.
Yeah, yeah. This is totally wrong. Okay.
When you do your partial fractions and you figure out what bx plus c is, you are going to get a linear expression over a quadratic that's irreducible. Anytime you have a linear expression over a quadratic that's irreducible, you should make a u substitution of the bottom and then try and turn your numerator into the derivative.
Okay.
All right,
So
do you have that matrix?
For the quiz?
Well, whatever, you said that you needed help with typing in something in your calculator, right?
Oh, yes, I have the quiz. So it's 1, the first column.
Okay, all right, so you have 1.
1, 1, 0, 2.
Wait.
Oh.
1, 1, 1.
No,
0,
not 2 times. Just 2 times. 1 is 2 times, yeah.
Okay. 1, 1, 0, 2.
Yes. 0, 0, 1, negative 1.
Okay.
And 4, 0, 0, 4.
Like that. Okay.
Yes.
So in my what kind of calculator are you working with?
So I got the TI-84.
Okay.
So I got the RREF part.
You're already at the RREF part?
Yes.
Okay, so you RREF parenthesis, you have to do bracket, bracket, 1 comma 1 comma 0 comma 2, close bracket, open bracket, 0 0 1 comma negative 1, close bracket, open bracket, 4 comma 0 comma 0 comma 4, close bracket, close parenthesis.
Oh, okay. So bracket and then close parentheses.
So the first set of brackets you have is to start the matrix, and the last bracket closes that matrix. Everything in between is just row, row, row. And then you also have to have the parenthesis that opens the function on the computer and that closes the function on the computer.
I understand. I know where I messed up. So it was always giving me an error.
Yeah. You'll get it now.
Yeah. Thank you.
Okay, no problem. All right, Abe, are you okay?
Yeah. Yeah, I think so. I'll see what I get.
All right, anyone else? Okay. Well, I'll leave the session open. If you all want, I can leave it open. It's up to you.
So we only have until 5.